So now, having defined momentum, let us define impulse as well. Impulse, yes, it's the product of force multiplied by the time during which the force acts. Very simple. Symbol, J. Notice the arrow on top, meaning it's a vector. Formula, J, or impulse, is force times time. Interaction time. Apply force to an object for 1 second, do it the same force for 2 seconds, twice the impulse. And as you can imagine, in most practical situations, that means the object is probably going to be moving faster with the greater impulse because you've applied the force for a longer time, enabling acceleration to occur for a longer period of time, etc. In any case, impulse is a vector, as I mentioned, and the units are Newton seconds. Newtons times seconds. But force, or newtons, is a kilogram meter per second squared, because it's MA. So if you think of MA, kilograms, A, meters per second squared, then you multiply it by seconds, and you get kilogram meters per second, which is the same as with momentum. All right, let's look at how we can represent impulse graphically. A force time graph, and here's an example of an actual somewhat complex force. And notice that this force versus time also has an area. There's an area under the graph. Now if we represent that same area with a constant or average force, we would get something like this. Here it comes, and there it is. So that rectangular region, if it's the same area as this original curve, then this represents the average force during that interaction. They have the same area. So we could represent that area in different ways. In other words, we can obtain the same impulse from in multiple different modes, so to speak. We could have this, a skinny rectangle, small amount of time, and a large force, of course.
Little t.
And then there's another way we could do it. Something like this.
Medium F, medium T.
You heard it. But we also could reduce that force, increase the time, and have
Little f.
So there you go. An impulse can be understood as the area under the force versus time graph. Notice that this, for instance, this big force for small time, that's kind of like having an auto accident and allowing the steering wheel to stop you. Not a pleasant thought, but nevertheless true. This one down here is more like having that same automobile accident and allowing the airbag to stop you. A smaller force, longer time, less damage to your body. So that's what you have an airbag for in the first place. That's the benefit of it. So you could definitely benefit from an airbag in such a situation. Same impulse, and actually same change in momentum as well.
Little t.
Medium F, medium T.
Little f.
So now let's clarify the relationship between impulse and momentum, as we've already alluded to. Newton's law, F equals ma. We'll start with that. And what is acceleration? Well, it's change in velocity over time. So F is equal to m delta v over t. We can multiply both sides of that expression by t and get F delta t as m delta v. I put the delta in t because this time is an interval of time during which the interaction occurs, during which the velocity changes of the mass. So the delta is kind of useful there. So the conclusion is this. Since we've defined F delta t as impulse and m delta v, m times v is momentum, so with the delta v, it's the change in momentum. Impulse is change in momentum, not just momentum. It's not correct to say impulse equals momentum, but it's how much the momentum changed. All right, so another form of Newton's law then since F delta t is m delta v is delta rho, change in momentum, then force, we can call force here, m delta v over delta t. So that's delta rho, or change in momentum over time. So basically what this says, and this is more in line with how Newton described it, he used calculus notation, but basically it's saying that the amount of momentum change is what equals the force. Specifically, the time rate of change in momentum equals the net force acting on an object. The rate at which an object's momentum changes is a direct measure of the net force on the object. Woohoo! That's pretty cool. And this is a little more general also because it's, as you look at delta rho, the change in momentum, momentum can change from two different things changing. Typically it's velocity, but what about a rocket ship where the mass that the rocket is made of is changing as well? So yes, both mass and velocity can change in general. Now when two bodies interact, the momentum of each one individually changes. The collective amount doesn't. The interaction types come in just a few categories. I'll just briefly list them. So we have inelastic. So when an inelastic collision occurs, it just simply means that they stick together. They go bonk. Well, whatever bonk is. But say an object that has a piece of clay on it hits another one, or a bullet gets embedded into a block. That maybe is a little more visual and graphic. And it sticks inside the block. Then we have elastic collisions. And an elastic, you know, something that's probably going to bounce. And in fact, that's exactly what it does. So a highly elastic rubber ball is one that bounces well off of the floor or the surface that it hits. So there's perfectly elastic, there's perfectly inelastic, there's also somewhere in between. But we won't worry about that as a category at the moment. Then we have explosions. And explosions are simply, you start from, say, well, it doesn't have to, but imagine starting from rest and having an object explode. You got pieces going in every direction. And so that takes a slight different form in terms of analyzing that kind of problem. But momentum conservation is maintained in all of these. And it can be in 1, 2, or 3 dimensions. We'll generally not be concerned with the more complex 3D collisions. But that is a situation where the conservation principle also holds true. Any situation, in fact.